Hello everyone, let's continue with our physics engine. Last time we created the vector class, and now we're going to start working with vector mathematics. So I'm going to make a mathematics class, or I guess a math class for vectors. Inside our physics library, I'm going to call this the flat math. And this is going to be a static class that's just going to contain a series of functions we can use to do mathematics with vectors. So I'm going to go ahead and write the prototypes here, and then we'll go through and write each one and see how they work. So first of all, I would like to create a length function. So this is going to return a floating point value that is going to tell us the length of a vector. So we'll just call this length, and it's going to pass in. We need to pass in the vector. And next, I also want to be able to get the distance between points in space, and that is simply going to be called distance. And that's going to take two flat vectors. And we'll just call those A and B. Let's see, next we need to be able to normalize vectors. And so when we normalize a vector, we're going to pass back a vector that has been normalized. So we'll just call this normalize. And then we'll pass in the vector that we would like to normalize. Let's see, so we have those three, and I think there are two more that we need. We need to be able to get the dot product, so let's make one of those. The dot product is going to return a floating point value, and to get the dot product, we need two vectors. And then we need the cross product, so that will also return a floating point value. And technically, the cross product isn't really defined in 2 dimensions, and so that's why we're returning a single floating point value. If you know anything about cross product, it's really a 3-dimensional operation. You know, I'm not perfect at math, but as far as I'm aware, it's mostly a 3-dimensional operation. We're doing a cross product. And I'm not sure if it exists in higher dimensions or not. It really doesn't exist in 2 dimensions. But in 2 dimensions, it can give us some interesting information if we take the cross product of 2 vectors. And so let's just go ahead and write the prototype here, and then we'll talk about it in just a little bit. So that looks like it. I think once you know all of these functions here, I think you're pretty much ready to go as far as doing everything you need to do with vectors. So let's go ahead and write the length. So the first thing I'm going to do is I'm going to go back into the game class. I'm going to make 2 vectors. Actually, I'm going to make 1 vector. I'm going to call this flat vector, and let's call this vector A. And I'm just going to set this equal to some value out in space. So let's just say that this vector is pointing at, we'll go over to, and remember, this is all going to be in meters. So let's just say it's 3 meters to the right and then 4 meters up. Now, in my initialization code, here's all the stuff I had before. They were testing the performance of our vector class. We can get rid of that. Don't need that anymore. And now I'm just going to use our shapes batching class to draw a line. And I can get rid of this circle that we were drawing before. But so let's draw a line that indicates the vector, or indicates what this vector looks like, this vector A. And so we're just going to use the shape batcher to draw a line. Now it's going to point from the origin because all vectors are relative to the origin. All right, so you're pointing from the origin to a point in space. Okay, and that's how we get the length. So let's go ahead and do this. This takes 2 vectors to draw a line segment. The first one is going to be the origin. So I'm just going to put a flat. So here's another issue that we're going to run into. So since we're developing a physics engine that's not specifically designed for monogame, it's actually designed to be more general purpose, we need to make some kind of converter to go from a flat vector to a monogame vector 2. All right, and so inside of our game project over here, I'm just going to make a new item, and I'm going to call this a flat converter. And this is going to be a static class that's just going to allow me to convert from one type to another. So maybe from a flat vector to a vector 2, or from a vector 2 to a flat vector as well. So this is going to be a static class, and right now it's not going to have a lot in it. The only thing I'm going to put in there is that I want to let's see, a static function I want to convert to a vector 2. And so actually I need to bring in the namespace for that. So that'll be Microsoft Framework. There we go. And we're going to return a vector 2, and we're going to convert to vector 2. And so we're going to pass in a flat vector. And actually I need to bring in that namespace as well. Okay, so there's the flat physics. All right, so the parameter we're going to pass in is going to be a flat vector v. And now this is going to be a really lightweight function. We're simply going to return a new vector, and it's going to be vx and vy. Okay, so just a simple conversion from one to another. In fact, what I may want to do, I'm thinking C#, the compiler will actually, it'll probably inline this anyways. But, I'm going to pass it a hint saying that I really would like the compiler to inline this function. So let's bring in the system runtime compiler services. And then for the method implementation, let's just give it a hint for the options that we would really like some inlining going on right here. Okay. And in fact, if I put this into release mode and I build, I'm just going to check out the IL code here real quick. So I got 2 failed, and that's probably because I've got some, this line right here doesn't work. Let's try that. So let's go ahead and build it. Got another fail. Let's find out where that error is. Oh, okay. So it's all of these functions that I'm just going to go ahead and comment these out for now. So we'll just do a if false. And so that'll get rid of all of that. Okay, perfect. So let's go ahead and now try to build it again. So now I want to go back to the flat converter. I want to look at the IL code for this. I have an extension installed called ILSpy. And so I can right click on the function that I want to look at and open it in ILSpy, and it'll give me what the IL code looks like. And yeah, if you look at this very, very small function, it's 18 bytes. I'm thinking the compiler would probably just inline this anyways, but I'm going to tell it that I really want the compiler to inline this. And now this still doesn't guarantee that it will, but let's go ahead and put that in there because I really would like that to be inlined every time. So back here, we're actually going to put the origin as the starting point. So let's put a vector 2 and 0, so that'll be the origin. And then let's use the flat converter to vector 2, and then we'll just convert the vector A that we had. And then finally the color, I'm just going to do white for now. Let's run it, and we should see, actually I'm going to put this back in debug mode, and let's run that. Okay, so there we go. That is the vector that represents 3, 4. And we can zoom in a little bit more here. So it's going 3 meters to the right and then 4 meters up, right, till it meets right there. Let's make that a little bit bigger, actually. So instead of 3 meters, let's do to the right, we're going to go 12 meters, and then up, we're going to go 20 meters. And let's just see what that looks like. Okay, that's good enough. Maybe I can zoom in just a little bit more. So instead of 5, let's make it an 8 times zoom. Okay, perfect. All right, so now let's start implementing these functions. So back in our flat math, I'm going to set this to true, so it actually compiles this. The first thing we want to do, well, actually, you know what? Let's move this down here. I'm going to keep this as false, and we'll just move this around to get rid of the code that we're not actually going to compile. Now, to get the length, what we're looking at is, let's bring up this, okay, we'll just throw a new not implemented exception, so it'll compile. So now when we get the length, what we're looking at is we want to know the distance from the origin to this point up here. And sometimes that's called the magnitude of the vector. So we want the length or the magnitude, or how far along is it to get to here. And basically what we're doing is we're just making a triangle out of this and then using the Pythagorean theorem. We're going to get the distance to get to the x from the origin, and then the distance to get to the y from the origin. And then we're going to calculate that diagonal using Pythagoras. So let's go back to our class here. First, we need to get the distance traveled on the x-coordinate, or the delta x. That'll be v dot x minus 0. And then the distance on the y is going to be v dot y minus 0. Oh, float it. these need to be floating point values. There we go. So now we have that, and then we just return, using the theorem, we multiply the x components together and then add that to the y components multiplied together. Now, this will give us the distance squared, and what we actually want is the actual distance. So we're going to bring in the math class and tell it we want the square root, and then we end up with this. Now, this is the actual distance formula. When we're calculating the length, we're calculating the actual distance that the vector is from the origin, or from 0. And if you look at this, this value of 0 doesn't do anything, right? If I'm subtracting, if I'm x minus 0 is just itself. And so I really don't even have to do this step. So I could just take that out. And then we're just left with Vx and Vy. And if that's the case, I don't need to store it in a local variable either. I can just put it right in here. So let's just do Vx, Vx, and then this will be Vy and Vy. All right, and so now that we have that, let's go back to our game class and let's just test it to see how it works. So inside this initialization function, once again up here, we're going to write out the length of the vector A. And then we'll just, let's tell it that we want to read a key and wait. Okay. Now it's giving me an error here because I think I have, yeah, I've got another library that has a flat math, and so I need to make sure it knows which namespace to use. So that'll be the flat physics, flat math. Okay. Okay, so let's go ahead and restart this and just see how it works. Okay, perfect. So it's telling me the length is 23.323807. So there's that one. Let's go ahead and work on the distance. Move this on down here. So distance, again, we already implement that, so let's just do it again. Now we're computing the distance between the ends of two vectors, which is our points in space. And so we need to calculate the distance between their x's and their y's. And so we're going to do the ax and the bx. That'll be the delta x. I call that delta x. That's the distance in the x coordinate. And then I'm going to the delta y. We have a delta y. That'll be the ay minus the by. And then we're going to do the same thing we did up here. We're going to return the square root of the x components multiplied together plus the y components multiplied together. All right. And again, that's just the Pythagorean theorem. You can look that up if you need further information. Let's move on to normalizing. Okay, now normalizing is kind of an interesting idea. Normalizing, vectors have a direction and they have a magnitude. So they point a certain way and they have a magnitude that tells you how far they point that direction. Okay, and with that, you can point to any space, any point in space. Okay, in our case, it's two-dimensional space, so we can point to any point in two-dimensional space. So what normalizing does is it takes that vector and magnitude, or that direction and magnitude, and turns it into a direction with a magnitude of 1. And the way that works is we first need to get the length of the vector. Let's go ahead and tell it we want to get the length. And we've already computed that up here. So come in handy, we can just call the flat math library and get the length of this vector. To make the magnitude 1, we have to divide each of the components of the original vector here by the length. So I'm going to make an x variable and say that's equal to v dot x divided by the length. And then the same thing with y is going to be v dot y divided by the length. And then we're going to return a new vector. That is the x and y. Okay, so very simple. That's what it looks like. I want to decrease the amount of code I have here. So instead of actually computing it here and then sending it in over here, I'm just going to put this right in the result. So let's take this and put it right there. And then same thing with the y. Let's just take this and put it right there. And we can get rid of this completely. We'll just leave that there. And now we have the dot product and the cross product. Let's go ahead and look at how the dot product is calculated. So first of all, there's this really neat website that I love. Math is fun, and they have all kinds of great information. Let's do the dot product. And if you have any questions about how the dot product works, or any of these things, vector math in general, this is a great resource. Here it has a great explanation of what the dot product actually is, and then here's how you calculate it. There's actually a way to use vector components to calculate this, and you can see it's just the x component times the x component of b plus the y component of a times the y component of b. And so I'm just going to go ahead and bring this in, and let's add it as a remark so I don't get this wrong. And we're simply going to return the a.x times the b.x plus the a.y times the b.y. And you can see, very, very simple function, but very powerful for what it gives us. So even if you don't have the exact answer in your mind, you want to get a general visualization of what is happening when you're doing these vector operations. And so we can go back in here, and I can just type, there's a viewer that somebody wrote on the internet. Let's see, it's called the dot product Java viewer, I think. I think that'll get me to it. Yep, that's the one right there. And if you look at this, it's going to show you the relationship, okay? So if you look at the green, you have a vector A and you have a vector B. And then down here, it tells you what A dot B is. It's equal to 1 right now. And as I move these vectors around, it kind of shows you what that looks like. And A dot B is actually this yellow line right here, okay? It's telling us this is where A dot B exists. And the neat thing about dot product is it gives us a couple of things. It tells us, it allows us to project one vector onto another. So right now I'm projecting this A vector, which is the red one, onto the B vector, which is the cyan colored one. One of the neat things about this is that it kind of gives me a relationship in their direction, right? So as long as I get a positive value in A dot B, they're pointing the same direction. The moment I get a 0 value, so we'll see if I can make a 0 or something close to a 0 value. So the moment it's 0, and it's, I'm not sure I can get this exactly, but see, it's real close to 0. They're perpendicular. And then the moment they are opposite direction, the dot product is now negative. So a couple of neat things the dot product can tell us there. And then finally, let's go ahead and implement the cross product. And I'm going to go to that same website. And we'll type in the cross product. There we go. Cross product. And then once again, if you want further information about what the cross product is or how it is actually calculated, great resource right here for how that works. Take a look at that. And then here's the calculating portion. Again, they have one version that uses the magnitudes and then the trig functions. We don't want that. We want the more simplified one. Now, if you remember, I was telling you that the cross product is not technically defined in 2 dimensions, right? In reality, we can still use it in 2 dimensions. And the reason is because we just treat the plane that we're rendering to as the z equals 0 plane, right? So we're on the z equals 0 plane. And if you look at these, if bz is 0, then this goes away because we're multiplying by 0, and then az is 0, so this goes away. And so the x component doesn't exist anyways in 2 dimensions. It just becomes 0. And same thing with the y. The az here is going to cancel out this because the az is going to be 0 because it's sitting on the z equals 0 plane. And then bz is going to be 0, so this is going to go away. And so the cx and cy result of the dot product don't even really exist. They're just 0. And so we can completely disregard it. And then what we really want is the z component, and that's going to be our result. So let me copy that, and I'll just bring it in here just to make sure I get it right. And so our results, we're going to return, it's going to be the ax times the by minus the ay times the bx. Okay. And once again, really quick, really efficient function. I'm also going to show you another viewer for this. So there's a Let's see, I think I call it cross product viewer. Let's see what happens with that one. It's going to show you what the cross product is actually calculating. And to be able to see it in your mind is a good idea. So what I'm doing here is I have an A vector and I have a B vector. You can see as I move these around, it's changing just, here's the result, and it's changing just the Z value, right? Because if you look at the 3D representation, it's all taking place on the 0 plane. And so these two values just go away and are 0. The cross product, you can see, is this Z result that's either pointing down or it's pointing up. It's pointing down or up depending on how these vectors are oriented with each other. If my A to C is on the left side of my A to B, I get a positive result here, right? So you can see the arrow pointing up. Also, my result over here is positive. The moment I go onto the right side, now it's negative, right? And so that's negative the whole time I'm on the right here. When I'm on the line, it becomes 0. So if we're pointing the exact same direction, we're going to get a 0 value. And then the moment I'm on the left again, I start getting a positive result. Okay, and so we can use this to determine our points, which side of the line our points on. It's really neat, and we're going to be using this a lot. That's pretty much it. That's the math library for our vector class. So let me go ahead and we have this vector A. I'm going to go ahead and make another flat vector, and I'm going to call this normalized. And that's going to be equal to, actually I got to do physics flat. Let's see, flat physics and flat math. And we're going to normalize the vector A. And then from there, let's go ahead and put, I'm going to keep this same line, and then let's draw another one with the normalized. So let's copy this, and now let's draw the normalized. And let's make it a different color. We'll do this one kind of a darker. Let's just do green and see what that looks like. And let's run that. Okay, so the first line is going to be the normal line. The next one is going to be a normalized vector, meaning it's going to be the same direction, but its magnitude is going to be 1. So it's going to be a lot shorter. And we are using meters, so it's going to be technically 1 meter. And let's go ahead and run that. And you can see there it is right there. So there's the original line, and then that green spot right there is our normalized line. And I can zoom in so we get a little bit better view of what that looks like. All right. So it looks like everything's working great. And in fact, you know what? Let me, I'm going to get rid of this console stuff here at the beginning. And then I'm going to draw a circle that has a magnitude of 1. Or I'm going to draw, has a radius of 1, so we can make sure this is working correctly. So let's draw a circle at the origin. So that'll be at the origin. It's going to have a radius of 1. Points doesn't really matter. We can do, let's do 24, and then the color is going to be blue. The radius of the circle should be the same length or the same size as this normalized vector. Let's run that and just make sure everything matches up. And it looks like it does. We'll zoom in so we get a better view of this. And you can see the radius is the exact length of 1. So perfect. All right, so it looks like that's our math library. We're ready to move on to the next step.